In this video, we're going to be discussing Gaussian elimination using matrices. Now, a matrix is in row echelon form if it has the following properties. First, that any rows consisting of zeros occur at the bottom of the matrix. Secondly, we must have that for each row that does not consist entirely of zeros, the first non-zero entry must be 1. And by the way, this is usually called the leading one. 1 for that row. Lastly, we also need that when we have two successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row. So we would have something like 1 entry, and then once we get down here, we would need a 0 there. We might have a 1 here, maybe we have a 0, but that would be okay. But then down here, if that's a 1, this would have to be a 0, and all of these would have to be zeros. And that's how our matrix would be formed. And we further say that if a matrix is in row echelon form, it is in reduced row echelon form if additionally we also have the following condition. Every column that has a leading one has zeros in every position above and below its leading one. To get a better sense of how row echelon and reduced row echelon form works and what it looks like, let's consider these examples. And for each one, let's determine whether it is in row echelon form. And we're going to go ahead and call this REF. And if it is in row echelon form, we'll then determine if it follows that additional condition to be in reduced row echelon form, which I'm going to call RREF. Okay? So here we go through and we say, well, is there any rows consisting just of zeros? And the answer is no in part A. So we don't have to worry about that first condition. The second condition says, do we have leading ones? Well, yes. Every first non-zero entry is a leading one. And then as we go down, we see that since there are zeros here, wherever there's not a leading one on this side of them, on the left side, then we say, oh, well, that actually is row echelon form. So this is in REF. Is it reduced row echelon form? And the answer is no, because there are not zeros everywhere else, right? So we would need zeros in all of these spots because there's no leading one there. So since there's no leading one, we don't have this being in reduced row echelon form. All right. So REF is a no. Here we ask so then what about for this one? Well, this is also, oh sorry, let's go in order. B is not in is not in row echelon form. And the reason it's not in row echelon form is that this list of zeros is not at the bottom. This row of nothing but zeros is not at the bottom. So it fails that first condition. Okay, thus it can't even be RREF. Okay, if we try row echelon form here, we say, oh well, there's a leading one, so we don't care about the rest. Zeros underneath it. Here we don't have to worry about anything, but there are zeros underneath it, and then 1 zeros that way. Look for our leading 1 zeros that way, 1 zeros that way. So this is row echelon form. Not reduced row echelon form because these aren't 0. Okay, just like this was not in reduced row echelon form because those aren't 0. This one is so again we have our leading ones, right? Zeros that fall at the bottom, so that's good. Here we notice this is what that we have zeros this direction, so it is in row echelon form. And it's also in reduced row echelon form because everywhere there's a leading one, we have zeros everywhere else. And so that would be reduced row echelon form. Is also a yes. Here, not in row echelon form because this is not a leading one. and thus it can't be reduced row echelon form. And then finally, this is in row echelon form because of the leading ones there, and zeros everywhere else, and on the left sides of the leading ones. And then you need, wherever, in any column where there's a leading one, we also have that there were zeros everywhere else, and so it's also reduced row echelon form. So we're good. And now, to get a better understanding of row echelon form or reduced row echelon form, go ahead and determine whether the following is in row echelon form, or whether and then if it is, whether it's in reduced row echelon form. On the count of 3, I will reveal the solution. 1, 2, 3. So this actually is in both row echelon and reduced row echelon form. It has the leading ones with the 0 column in the bottom, so it is row echelon. But here we see that it is also in reduced row echelon form because anywhere that we have a leading one, we have zeros everywhere else in that column. And now, at long last, we come to solving a system of equations using Gaussian elimination, but we're going to do it using just the augmented matrices. All right? And so the goal here is to get it into row echelon form. Okay? So we're going to write this as an augmented matrix and then try to get it into row echelon form. That way we can back substitute. So if I write out this augmented matrix, I have 0, 1. So 0, 1. Give me space so I can do my row operation. 0, 1, 1, -2, and then -3. Going down, we have 2, -2, -19. And then filling out the rows, we have 1, 2, -1, 0, 1, 2, -1, 0, 2, 4, 1, -3, and 1, -4, -7, -1. All right. And now we're going to start doing row operations. It'd be useful, so thinking about this, it'd be nice to have the one up there to help eliminate and get zeros in the rest of the column. So I'm going to go ahead and do an interchange first, okay? So by swapping those rows, and to be consistent with the book, let me write it this way. So we're going to swap the top 2 rows. So swapping row 1 and row 2. We now get that, yeah, I'll write it exactly how the book does it. R2 and R1, so we swapped them to opposite places. So this will be 0, so this will now be 1, 2, -1, 1, 2, -1, 0, -3. Then we have 2. Then we have 2, 4, 1, -3, -2, or no, -3, sorry, I messed this up. I did the 3rd row. So, 0, 1, 1, -2, -3. So this would be +2. All right, now I'm on track. The other rows will stay the same. So 2, 4, 1, -3, -2, and then 1, -4, -7, -1, -19. All right. And then what we're going to do is we're going to do a couple of things next. We're going to go ahead and I'm going to do 2 row operations because I want to zero out both of these, okay? To zero out both of those, what I'm going to go ahead and do is I'm going to go ahead and do, I'm going to add -2 times row 1 and add it to row 2. So here if I have 1, 0, and then so -2 times row 1 added to row 2 here. And then I'm going to take negative row 1 and add it to row 3 to get a new row 3. Doing so, I'll have, so these would stay the same. But now these, when I actually do that out, I get, for my second row, that zeroes out. This will also zero out. I'll get a 3 here, and I just lost a bunch of stuff. Sorry about that. So I was wondering why it was so small. -1, 0, -2, 2, 3. There we go. So 0, 0, and then I would get a 3, a -3, doing the addition, and a -6. And then when I take this row, when I took this row times 2, and when I subtract this row from that row, I'm going to get 0, 0, -6, -6, -1, -21. All right. The next goal is to eliminate this -6 here to make all zeros there. Doing so, I end up with, so what would I do? I would take 1, if I take 1 times this, I won't affect anything here because the 0, so I won't have to worry about adding there and messing this up my work. But I'm going to go ahead and take -6 times, +6 times row 2 and add it to row 4. This was row 3 and that was row 4. Sorry about that. 6 row 2, add it to row 4. So I have 1, 0, 0, 0. Then I will have, so I have 1, 0, 0, 0. I need room. And then, let's make it a little bit bigger. Okay, 1, 0. So the top won't change, right? The top 3 rows. So 0. Right there. And then, so 2, -1, 0, 2. 3, -6 here. -2, 1, 1, 0, 3, -3. But the bottom row changes. Doing that, that's going to zero out. There I'm going to have 6 times that, so that's also going to zero out. And then I'll have a -13 and a -39. And lastly, I'm going to take 3, I'm going to take 1/3. I'm going to divide this by 3 and divide that by -13. So I'm going to have my same rows, but this time, and I can go ahead and use zeros there as a placeholder, just trying to create everything and have it all set up. But this row, I'm going to have it as R 1/3 R3. And then, so I'm dividing by 3 to get rid of the 3 to make a leading 1 there. And to make a leading 1 there, I'm going to do -1/13 R4 and replace row 4 with that. So I'd have 0, 0, and everything works out pretty well. 1, 1, 1. These, of course, don't change. -1 there. Sorry, and that should be a +2 and a -1. 0. -2. That'll become a -1. That would become a +1. That would become a +3. That divided by +3 is -2, 3, and 2. And now what do I have? Well, if I write this out, what I have here using the first equation is that W equals 3. So if I was to actually write out the system, what I have now is x plus 2y minus z. So what I did is I basically did, I did my Gaussian elimination on all of this, but instead of manipulating the equations, I just manipulated the rows using row operations. And by doing so, what I now have is I can go back to my system, and I was able to kind of get it down to this, this form, where I can do back substitution, but luckily I was able to do all of that without ever having to use the variables. So, plus z to w equals -3. And then we have z minus w equals negative 2, and then w equals 3. So we have that as my system, which means I can back substitute. W is equal to 3, which means plugging that into there, z minus 3 equals negative 2, which tells me z is going to equal 1. Back substituting again, I have y. I'll eventually get y plus 1 minus 2 times 3 equals negative 3. That's going to be negative 6. Add that to that side, you get positive 3. Subtract a 1, you're going to get positive 2. So y equals 2. And then finally, for x, we would have x plus 2 times 2 minus z, which is 1, equals what? Equals 2. Solving out for x, you'll end up with x equals negative 1, right? And so our solution is negative 1, 2, 1, 3. All right, and now it's time for you to try an example. Go ahead and solve this using augmented matrices. Go ahead and solve the system using Gaussian elimination. On the count of 3, I will reveal the solution. 1, 2, 3. So as you see here, things can get a little bit more complicated. If you're insistent about doing this properly, you'll end up with some fractions. And so just be careful is what I suggest here, okay? I did make a mistake somewhere. I'm not sure where, but I did make a mistake because if you try this out, this doesn't solve the first equation. It does, so 24 minus 8, 24 minus 4 plus 4. Yeah, so it doesn't solve any of the negative 18 minus 4 plus 4. Yeah, so I made a mistake somewhere. I'm not sure where, but I made a mistake somewhere. So sorry about that, but it's still a good example for how this process works, even with fractions. So in summary, we have the following process that we use to solve a system of equations with Gaussian elimination and back substitution. First, we write the augmented matrix of the system of linear equations. Then we use elementary row operations to rewrite the augmented matrix in row echelon form. And then we write the system of linear equations corresponding to the matrix in row echelon form and use back substitution to find the solution. Now, in practice, once you get used to it, this methodology actually goes a lot quicker. It helps if you do a few steps at the same time, like with most mathematics. However, so for instance, let's try this one out. So if we write out the augmented matrix, we would have 1, 1, 2, 3, negative 1, 0, negative 3, 2, 2, 1, 5, negative 1, and then 4, 6, 4, 1. Here, we want to make all of those zeros. So what can we do to make all of those zeros? Well, to make this one, negative 2, let me finish writing this out. To make this one a 0, we would need to subtract equation 1 from row 1 from row 2. So negative row 1 plus row 2. And doing so, we end up with 0, so 0, negative 1, negative 1, 2. We also want to make this run, the third row, the first entry in the third row 0. To do that, we would need to take negative 2 times row 1 plus row 3. Doing so would give us 0, then a negative 1, and then a 1, and then a negative 4. And then finally, to make this one a 0, we would need to take negative 3 times row 1 and add it to row 4 to get a new row 4. So we would have, if we did that, we'd have 0, 5, -7, and -11. And like that, we now have our first column done. What about the next column? Well, here we need to make both of those 0. If we go through and we do so, we would need a 1, we'd have -1, -1, 2, 4, that row's done. This row is also now done, well, except we'd like a 1 there. So -1 and 2, and then for this row, we could subtract that row to get this one. Oh, and this should be a positive 1. I don't know how I got a -1 there. Sorry about that. Positive 1. So this is also a positive 1 there. And so, but if we do that, we end up with 0. So here, to eliminate this, to make this a 0, we would need to add row 2 to row 3 to get a new row 3, which would create a 0 there. Adding there, we get a 0, and adding there, we get a -2. And now it actually doesn't matter what we have, because if you look here, what this is this is actually the equation 0 equals -2. And because of that, that's an equation that can't be satisfied, so there's really no solution to this system. So that's actually kind of a nice place that we can stop once we run into something like that. And finally, one more system to work. Go ahead and try this one out for yourself. On the count of 3, I will reveal the solution. 1, 2, 3. So here, if we write this system out into the augmented matrix, we have this. We go ahead and we do row operations to get rid of to create zeros there. Then we continue, since we already have a 1 there, to create a 0 here. But when we do that, we end up with an equation of 0 equal 2, so there's no solution to this system either. For more practice in working out some Gauss-Jordan elimination problems, be sure to see the textbook pages 549 through 551 and work the associated exercises. In our next video, we're going to streamline this process a little bit further still to be able to avoid back substitution using something called Gauss-Jordan elimination.